So hello everyone, I'm Norman Wahlberger. Today we're going to have a look at some basic counting and probability. Counting is sort of the essence of probability. So the kinds of things that we're going to be counting are, for example, words. So let's count the number of words of length, say k, that are possible with n letters. So we have, in this case, k would be equal to 5. And maybe we have n letters. The letters might be A, B, and C. So n would be 3. And then we're asking how many words can we make. And word here just means some combination of the letters. Doesn't have to mean anything. Okay, so here this is obviously pretty simple because there are 3 choices for this one, 3 choices for this one, and so on. So altogether, the number here is 3 to the 5th. And in the general situation, if we have words of length k with n letters, then we have n to the k. N choices at each possibility. So it's n times n times n times n all the way up to n to the k. All right, so that's the first simple example. The next one that we'll look at is to count words of length k from an alphabet of k letters, so the same number of the length of the words are going to be the same as the number of letters, with repetitions not allowed. That's a basic kind of problem. So for example, we could have, if k was equal to 5, we're talking about how many words of length 5 from an alphabet, say A, B, C, D, E. But this time we're not allowed any repetition, so each word, each letter can only be used once. So that means every letter will be used exactly once. So we're really just talking about permutations. So we're talking about a permutation of k objects. That's another way of saying it. And the number here is, well, there's going to be, in this case, 5 choices for the first letter, perhaps D. And then once we've picked D, we're not allowed to use it anymore. So for the next choice, there's going to be 4 possible choices, maybe B. So there's going to be 5 choices here, times 4 choices here, times 3 choices, times 2 choices, times 1 choice. That's how many choices there's going to be. All right, so the number is k times k minus 1 in general, times k minus 2, all the way down to 1. And that's k factorial. Okay, a slight variant on that is the number of words of length k from an alphabet with n letters. Again, repetitions not allowed. All right, so now there's n possibilities. So there's n possible choices for the first letter. And then once we've used that letter, we're not allowed to use it anymore. So at the next stage, we have only n minus 1 to choose from. And it keeps going down like this until we get to the last kth letter in our word, because our word has length k. So we're going to have to go down to n minus k plus 1 to ensure that there's altogether k terms in that product. And one way of writing that in terms of factorials is to write it as n factorial, which is the product of all the numbers from n down to 1, divided by the next one here, which would be n minus k factorial. Okay, then the next counting one, which is again related to this one, is the number of subsets of size k number of subsets of size k from a set of n elements. All right, so for this kind of question, we probably want the set that we're choosing from to be bigger than or equal to k. Okay, so how are we going to think about this? So maybe I'll give a... No, we'll just do this. The number of subsets of size k from a set of n elements. We can think about this in terms of the number of lists. So we're talking about subsets, so we're not allowed to repeat anything. So if we count lists first, so the number of ordered subsets, or lists, is what we just calculated in the previous one. That's the number of ordered subsets of k elements from n. Now for each one of these ordered subsets, we can permute the elements and get a different ordered subset. So to get the number of subsets, we should divide this number by the number of ways of permuting these k objects. So to get the number of subsets, we divide by k factorial, which is the number of ways of permuting those k things. And so the number that we want, therefore the number of subsets of size k from n elements is this number divided by k factorial, which we'll write as n factorial over n minus k factorial times k factorial. And of course, that's usually called a binomial coefficient, n choose k. Okay, so we say n choose k, and that just represents exactly what we're doing. We have n things, and we have to choose k. And that's the number of ways of doing that. So, for example, 5 choose 3, what would that be? That would be 5 factorial divided by 3 factorial divided by 2 factorial. All right, the easiest way of computing this 5 factorial over 3 factorial is the same as 5 times 4. So it's 5 times 4 over 2 times 1, which is 10. And if the set was, say, A, B, C, D, E, then you might like to count all the subsets and check that there are, in fact, exactly 10 of them. So the counting would start like this. The first one would be A, B, C. And then another one might be A, B, D, and so on. If we count the number of subsets, you should get 10. All right, we're going to see this kind of argument and these kinds of numbers appearing quite a lot in probability. So let's have a look now at just basic definitions of probability. Okay, so there's lots of different ways of thinking about probability. We're going to adopt a kind of a mathematical one, which is a little bit idealized. Okay, so we suppose that we're interested in a certain outcome. Let's call the outcome O. Okay, a certain outcome O results from n ways out of t possibilities. All right, so there's some space of possibilities. This is very general. Okay, and there's altogether t things here. There's these t possibilities. And we're going to assume that they're all equally likely for now. Okay, so these are all equally likely. Now we're interested in a certain outcome, which is perhaps something like this. This is our outcome O. Okay, we're interested in when does this particular outcome occur out of the total number. So there's a certain of the possibilities correspond to this outcome, and these are n in number. Okay, so we're going to suppose that out of the whole t possibilities, n of them correspond to our outcome that we're interested in. In that case, we say that the probability, and I'll just write short like this, the probability of O is, by definition, the number of ways of getting O divided by the total number of possibilities altogether. This is a number between 0 and 1. If we call it P, then P is always between 0 and 1, because we're always talking about positive numbers, and T is at least as big as N. Okay, so probability first occurred, no doubt, with gambling. It's probably been around for thousands of years, really. But it was kind of mathematically studied in the 16th century. People started thinking about things 16th and 17th centuries. Okay, so let's do some examples. Okay, the simplest one is probably rolling a dice. So if you roll a dice, then the probability of the outcome, say, getting a 3, rolling a 3. Well, a dice has 6 sides. 1, 2, 3, blah, blah, 6 sides. So there are 6 possibilities altogether. And we're only interested in the one possibility that makes a 3. And so the probability of getting a 3 is 1 over 6. How about something a little bit more fancy? So, second example, in a class of, say, 28 people, let's say 4 have red hair, then the probability of choosing a random person, the probability of a random person having, let's say, red hair, I'll just write it like this, is, well, out of the total of 28, there's 4 that match the outcome that we're interested in, that we're looking at. And so the probability would be 1/7. Okay, some other examples. The probability that you get 3 successive heads if you flip a coin, flip a coin 3 times. So we flip a coin 3 times and we want to know what's the probability of getting 3 successive heads. Well, to do that, we have to just remember that all the possibilities are represented by those 8 things that we talked about last time. So H, 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 T, and so on. And there were 8 of them. And we're interested in this particular outcome. And so the probability is going to be 1 out of 8. Another example, one that's important if you play certain games like backgammon or something like this. If you roll 2 dice, and let's let P be the probability of getting a total of 8. Okay, you roll 2 dice and say, what's the probability of getting a total of 8? Well, in this case, the space of possibilities is really all the possible pairs that you can get for the 2 dice. So the 2 dice might be might be a 1 and a 4. That might be one possibility. Altogether, there are 36 different possibilities for the 2 dice, starting from, say, 1, 1, then 1, 2, all the way up to 6, 6. And each of those possibilities is equally likely. And we're interested in an outcome, well, the outcome of the ones that add up to 8. So we're interested in the outcome that's represented by the set 2, 6, or 6, 2, or 3, 5, or 5, 3, or 4, 4. Those are all the possibilities of the 2 dice landing that will generate a total of 8. And there are 5 such possibilities, as we can see. So the probability P is 5 over 36, which is roughly 0.1389. Okay, so there's various rules of probability that help us calculate more complicated probabilities. So let's have a look at these rules for probabilities. All right, so the first one is called the negation rule. And it's a very simple one. It says that if the probability of an outcome O is P, then the probability of O not occurring is 1 minus P. Also, for example, the probability of rolling a 3 is 1/6. So therefore the probability of not rolling a 3 is 5/6. Our second rule is the multiplication rule. Okay, so it's a little bit longer. So if we have two possible outcomes, so if O1 and O2 are independent outcomes, and I'll have to say a little bit about what that means. So if they're independent outcomes, that means that knowing one does not influence the other. Okay? So knowing one doesn't influence the other. Then the probability of O1 and O2 occurring is the probability of O1 times the probability of O2. So for example, if we're playing cards, and I want to know what's the probability of drawing a red face card. Okay, a face card is Jack, Queen, or King. And when I say red card, I mean hearts or diamonds. Okay, so what we have here is sort of two different pieces of information. One is that we want a red card, and the other one is that we want a face card. And those are independent events, or independent outcomes, in the sense that if you know that you have a red card, it doesn't tell you anything about the probability of having a face card. A face card is neither less or more likely if you happen to know that the card is red. Okay. So according to the probability, this multiplication rule, the probability should be the product of the probabilities of getting a red card times the probability of getting a face card. What's the probability of getting a red card? Well, there's 4 suits, and we're interested in 2 of them, so 2 out of 4, that's the probability of getting a red card. And the probability of getting a face card, just by itself, well, there are 13 possible values for the cards, ace, 2, 3, up to king. And we're interested in 3 of them, Jack, Queen, and King. So the probability of a face card is 3 over 13. The probability of a red card is 2 over 4, or 1/2. So the probability of a red face card is the product of those, which is, simplify, 3 over 26. Okay, there's one more main rule, which is the addition rule. If an outcome O can occur in 2 or more distinct possible ways, then the probability of O is the sum of the probabilities of each of the individual ways of getting O. So here's an example, a little bit more sophisticated this time. So suppose we want the probability of getting exactly two 3s if we roll a dice 5 times. Okay, you're going to roll a dice 5 times. And you want to know what's the probability that you end up getting a 3 exactly twice. Not once, not 3 times, exactly 2. But where the 2 3s occur, that doesn't matter. Okay, so let's look at this in sort of stages. So the probability, let's say, of getting a 3 in exactly, let's say, the first and fourth positions, or first and fourth rolls, would be what? Let's just calculate that as a starter. The probability of getting a 3 in exactly the first and the fourth rolls. Okay, well, there's 5 individual things that are happening. So we're saying, all right, what's the probability of 3 occurring in exactly, first of all, in the first roll? In the first roll, there's a 1 in 6 chance of getting a 3. All right, so that's the probability of getting a 3. And then we're interested in the probability of the next roll of not getting a 3. So we have to multiply that by 5, 6, because that's the number of ways, that's the probability of not getting a 3 on the second roll. On the third roll also, we're not going to get a 3. So this is no 3. Here's no 3. And then on the fourth roll, we're supposed to get a 3, so we have to multiply by 1/6 again. And then we have to multiply by final 5, 6 for that last fifth roll. So that product, which is really the multiplication rule, okay, that would be the answer to the simpler question of what's the probability of getting a 3 in exactly the first and fourth positions. Okay, now we're interested in this slightly more complicated question of getting a 3 in any 2 of the positions. So what we have to do is we have to repeat this argument, not just for the positions 1 and 4, but also for the positions 1 and 3 and 2 and 5, and in fact all possible positions. So we have to repeat for all possible positions, or for all possible pairings. And how many of those pairings are there? Well, that's a question of asking how many ways are there of choosing 2 out of the 5. I happen to have chosen 1 and 4 for my first example. But altogether there are 5 choose 2 possible ways of choosing 2 out of 5. So we have to repeat this for all possible pairings. So there are 5 choose 2 such possibilities or such probabilities. And the addition rule says we have to add them all up. So the final probability, well, since they're all going to be the same, they're all going to look exactly the same except the positions of the 1/6 are going to be in different spots. But the final probability is going to then be 5 choose 2, because that's how many there are, times 1/6 squared times 5/6 cubed. Do I happen to know what that is? Yes, I think it's 0.161, roughly. 0.161. So maybe a 1 in 6 chance getting exactly 2 3s. This kind of this form of this probability is sometimes called a Bernoulli probability, or sometimes a binomial probability, because it's a lot like a binomial sort of theorem. There's a 3 here. That 3 is an exponent. All right, so let's make a calculation that's important for poker players. Now that we have some experience, we'll make a poker calculation. Any of you play poker? All right. Okay, so here's a question. What is the probability of getting at least one pair from a 5-card hand out of a deck of 52? So you're dealt 5 cards in a typical poker game. You're dealt 5 cards. And the question is, what is the probability that that hand that you have has at least a pair? That at least 2 of them are the same, like 2 kings or 2 9s. 3 would be also included in this. Well, let's call this probability P, so it has a name. Then 1 minus P is the probability of getting all cards of different values. Let's calculate this. What's the probability of getting a hand with all the cards of different value? So no repeated 4s or no repeated jacks or anything like that. Okay, so there's going to be 5 things that we're going to multiply, because you're going to be getting the cards one at a time. The first card is just completely random. You're going to get a card with probability 1. Okay. Now, for the second card must, if we're wanting to get a hand like this of different values, that second card better not have the same value as the one that you've just gotten. So what's the probability of that happening? Well, let's say you've just gotten a king. There are now 3 kings out there in the deck. You've just been handed 1 card. There are now 51 cards left, and 3 of them are kings. We want to not get one of those kings. So the probability of not getting one of those kings is 48 out of 51. Okay, so this is the probability of not getting your first card on your second card. Okay, now you've gotten 2 cards, maybe a king and a 4. What's the probability that the third card still is different from the ones that you've got? So you've got your king and a 4. So out of how many cards are left? There's now 50 cards left. And out of those 50, you do not want to get, or we're thinking about not getting another king or another 4. So there's 6 of them that have to be ruled out. So there's going to be 44 that will lead to you getting a different third card. And then for the next one, it will be 49. There'll be 49, and there'll be 40 cards. It goes down by 4s. And then the last one, 36 out of 48. Multiply all those probabilities, we get 2,053 over 4165, which is roughly 0.4929. And so the probability P is 1 minus that. Is 1 minus this 0.4929. So it's almost equal to a half. Pretty close. So you dealt a 5-card hand. The probability of having a pair or better is pretty well a half. So good poker players know lots of probabilities, not just baby ones like this, but lots of more serious probabilities associated to the game. All right, let's have a look at some maybe more curious probabilities. Just to get used to thinking about these things. And I want you to get thinking about the idea that there's probabilities all around you in the world. There's probabilities everywhere around us. We're just not really aware of them. But we can ask questions and investigate all kinds of things from a probabilistic point of view. So let's have a look at this question. Let's call it common birthdays. So the question is, what is the probability that of 10 people in a room, at least 2 share a birthday? If I take a random sample of you, 10 of you, and the question is, what's the probability that if we check out all your birthdays, that 2 of you, at least, will have the same birthday out of that 10? It's a little bit unlikely, right? We don't expect it to be too common because there's 365 possible days. We'll forget about leap years. Okay. So let's call this probability P. So let's find rather 1 minus P, the probability that all 10 have distinct birthdays. Well, sometimes it's easier to count the opposite or the negation. So we're going to think about counting or finding the probability that all 10 have distinct birthdays. Okay, so, well, this is, you have 10 people. Each one of them has a birthday, which is some number between 1 and 365. So the total number of possible outcomes of those 10 people is 365 to the 10. That's how many different possible birthdays we could assign to these 10 people. Now, how many of them are going to result in distinct birthdays? So now we're going to just count up here the possibilities of those 10 people that actually will contribute to having distinct birthdays. So the first person, well, they can have their birthday whenever they want. Okay, but if we want distinct birthdays, then the second person that we ask had better have a different birthday from the first one. So he or she only has 364 possible birthdays to have. And then the next person, well, 2 birthdays have already been ruled out, so now there's only 363. And so we have to multiply the top 10 numbers, starting with 365 and going down to 356. And when we calculate this with a calculator, this is roughly 0.883. And so therefore, P is 0.117. As a little exercise, you can check that that 23 is kind of the magic number here. With 23 people, the probability P is just a little bit more than a half. If you have 23 people, then there's pretty well a 50-50 chance that at least 2 of the people will have a birthday in common. Okay, I want to say just a little bit about odds, because a lot of times in the sporting betting world, probabilities are expressed in terms of odds. So odds are the things that bookmakers deal with. Odds are very close to being like probabilities, but they're just slightly different because there's sort of a monetary aspect. All right, so let's say a simple example. You roll a dice, and then we've said that the probability of getting a 3 is 1 out of 6. The bookmaker would say that the odds, and sometimes this word against is thrown in here, but not always. The odds against the event, the odds against the outcome are 5 to 1. What does that mean? That means if you're going to make a bet with the bookie, okay, that means that you put up this amount of money, and this is the amount of money that the bookmaker puts up. So the bookmaker will say, all right, the odds are 5 to 1, you pay me $10, you roll the dice. If you win, I'm going to give you your $10 back and 50 of my dollars. The bookmaker matches your $1 with his $5, and the winner takes all. This is actually this is actually the true odds, because if you played this game a lot, you would break even. Right? 1 out of 6 times you would win. So 1 out of 6 times, if you played it 6 times, 1 out of 6 times you would win on average, and you would win your $1 back and your the bookmaker's $5, so you'd have $6. The other 5 times you would lose your $1. So on the average, you would still be just exactly where you were before. Now, of course, a bookmaker is not interested in offering you this bet. Right? Bookmakers are not. What's the point? The bookmakers will happily offer you 4 to 1. I'll offer you 4 to 1. Right? That's how the bookmaker makes their money. Because the odds that they're paying are not quite up to the level of the true odds. So in general, if there's a probability, if the probability of an event is P, then the odds against it, or just the odds, are 1 minus P to P. So for example, if P is equal to 1/6, then the odds are 5/6 to 1/6, which is the same as 5 to 1. Okay? This is how we calculate the odds given the probability. And often this is written, because it's just the ratio that matters, it's written in the form R to 1, 5 to 1, 100 to 1. So R here is, well, with the ratio 1 minus P to P, because this R to 1 has to be the same as 1 minus P to P. And so this formula, simple formula, allows you to convert between probabilities and odds. Okay, so R is equal to 1 minus P over P, and if you solve for P instead, you can see that P equals 1 over 1 plus R. So if you know what the odds are, then you can calculate the probability pretty simply. So for example, if the odds are, if black caviar races again, okay, so maybe the odds then would be what? Let's say if we have a very poor horse. So the odds of say white caviar. So if the odds of white caviar are 100 to 1, okay, then that's really saying that the probability of white caviar winning is 1 over 101. Okay, but so for black caviar, if the odds of black caviar are, maybe it's more like 2 to 5. What's that mean? That means the bookmaker will take your money. You pay $5. You give the bookmaker $5, and if black caviar wins, he'll give you your $5 back and $2. Okay, actually that's probably not bad for black caviar. Okay, so in this case the odds would be 2/5. That's like 2/5 to 1. The odds is 2 over 5. And so the probability, according to this, would be 1 over 1 plus 2 over 2/5, which I guess would be 5/7. So the odds of 2 to 5 would correspond to a probability. The bookmakers think that the probability of black caviar winning would be 5/7. Of course, in the last few races, the black caviar race, the probability was much closer to 1. You wouldn't have gotten anywhere near odds of 2 to 5. All right, so next time we're going to start moving to the more mathematical framework for probability theory involving sample spaces, and we'll talk a little bit about different sort of theoretical aspects of the subject. So we'll see you then.